For more than 100 years, the way we've made power has been pretty much the same. You get something hot, you boil water, and you use that steam to spin a giant turbine. But that entire age, the age of steam and turbines, well, it might be coming to a very quiet, glowing end, all thanks to a totally revolutionary new way of thinking about energy.
Just think about that for a second. No spinning blades, no high-pressure steam, no deafening noise. Just a hot object on one side and pure, clean electricity coming out the other. It really does sound like something out of a sci-fi movie, right? But believe it or not, this is becoming a reality.
And this chart really gets to the heart of it. On the left, you've got the old guard, a massive, complicated mechanical beast of a system. And on the right, you have the Challenger, an elegant, simple, totally silent, solid-state solution. This is the fundamental shift we're going to dive into.
So, to really get why this new tech is such a big deal, we've got to first understand the limits of what we're using right now.
Look, steam turbines have been absolute workhorses for our civilization. There's no denying that. But at their core, they're 19th century technology. They waste a ton of energy just as heat and friction from all those moving parts, and because they have moving parts, they need constant and very expensive maintenance. But here's the real kicker. They just don't scale down. You can't shrink a giant power plant turbine to run a single house or a remote village. It just doesn't work.
Okay, so if turbines are hitting their limits, what's next? Well, this is where a wild idea called thermophotovoltaics, or TPV for short, steps onto the stage. And it works on a completely different and way more direct principle.
Honestly, this is the best way to wrap your head around it. You already know how a solar panel on a roof works, right? It's designed to capture photons coming from the sun. A TPV cell does the exact same thing, but its sun isn't 93 million miles away. It's a man-made heat source, like a glowing hot block of metal sitting right next to it. Now, the one key physics concept you need to know is something called the band gap. And don't worry, it's not as complex as it sounds. The best way to think of it is like a bouncer at a super exclusive club. A photon, a particle of light, has to show up with exactly the right amount of energy to get in. If it has too little energy, the bouncer just ignores it and it passes right through. If it has too much energy, it gets in, but all that extra energy just gets wasted and turns into more heat. It has to be just right.
So the whole thing is this really elegant three-step dance. First, you heat something up until it's glowing white-hot. That hot object starts blasting out a flood of infrared photons. The TPV cell, which is specially designed with that perfect band gap, acts like a net, catching only the photons with the right amount of energy. And boom, when those photons hit, electrons are knocked loose, and that flow of electrons is an electrical current. It's that direct.
Okay, so what does one of these setups actually look like? Well, it really boils down to 4 essential parts that have to work together perfectly.
You've got the heat source, our mini-sun, you've got the TPV cell that does the magic conversion, and you need a heat sink to keep the cell cool and efficient. But the real genius here, the unsung hero of the whole system, is that spectral filter. Think of it as a super smart gatekeeper. It lets all the photons with the right energy pass through to the cell, but it reflects all the wrong ones right back to the heat source. This recycles their energy, keeping the source hot and making the whole system way more efficient. It's an incredibly clever design.
Now, for the longest time, this was all just a really cool idea stuck in a laboratory. The performance, well, it just wasn't there. Until very, very recently.
And that was the big roadblock, right? For most of its life, TPV was just inefficient. It could only convert less than 20% of the heat into usable electricity. That made it interesting for scientists, sure, but totally impractical for the real world. It was a neat toy, but it wasn't a serious tool.
And then, a team of researchers from MIT and NRL hit this number, 41%. Let me be clear, this isn't just a small improvement. This is a phase shift. This changes absolutely everything.
So why is that one number such a massive deal? Well, look at this. For the very first time in history, a solid-state heat engine with 0 moving parts has officially surpassed the efficiency of the average steam turbine that powers our world. This is the moment TPV graduated from a lab curiosity and became a serious, major contender for the future of energy.
So how on earth did they do it? It was basically 2 incredibly clever engineering hacks. First, instead of just one material, they stacked multiple different semiconductor materials on top of each other. Each layer was tuned to catch a different flavor or energy level of photon. Second, they put a tiny gold mirror on the very back of the cell. Why? So any photon that managed to get all the way through without being absorbed gets bounced right back for a second pass. It's all about giving every last photon a chance to do its job, its maximum efficiency.
Okay, so we've got this super efficient new technology. That's fantastic. But what can we actually do with it? Well, this is where things get truly exciting and a little bit mind-bending.
In fact, when you hear researchers talk about one application in particular, they use this exact phrase. They call it the holy grail of energy storage, and for a very good reason.
This is it, the thermal battery. The concept is almost beautiful in its simplicity. When you have tons of excess renewable energy, when the sun is blazing or the wind is howling, you use that cheap electricity to heat up giant, heavily insulated blocks of graphite to thousands of degrees. They just sit there, holding all that energy as pure heat. Then, at night, when you need power, you just expose the TPV cells to those glowing hot blocks. It's a battery with no complex chemistry. It's potentially way cheaper than lithium-ion, and it could last for decades.
But it doesn't stop with grid storage, not even close. Imagine lining the smokestacks of steel mills and glass factories with these TPV panels. You could capture all that wasted heat that's just being vented into the atmosphere and turn it into free electricity for the factory. Or think about deep space probes. We could power them far more efficiently than we do now, allowing us to explore the darkest, most distant corners of our own solar system.
Okay, now let's be realistic. This isn't a perfectly smooth road from here on out. There are still some pretty significant engineering hurdles that we have to clear before you see TPVs in every power plant.
For one thing, the exotic materials they use, like gallium and indium, are a lot pricier than the good old silicon we use in solar panels. Then there's the heat problem. Trying to keep one side of your device cool when it's literally inches away from a 2,000-degree heat source is, as one engineer put it, an engineering nightmare. And of course, there's the big one. We need to figure out how to mass-produce these highly advanced cells cheaply and reliably.
But if, and it's a big if, but if these challenges can be overcome, the potential is just hard to overstate. By basically cutting out the middleman, the turbine, we found a simpler, quieter, and frankly, more elegant way to turn heat directly into power. So the next time you think about the future of energy, don't just picture wind turbines and solar panels, picture a silent, glowing brick that might just change the world.